Okay, so we were talking about the computational complexity of learning, and we saw some examples, some positive examples, some examples in which we could have efficient algorithms, but the examples were different in some some subtle ways. They were different, and I want to turn the light to these differences. So we saw several examples, but they differed across two axes, at least. One of them is the question of whether, so our task is we get a sample, and we are trying to learn based on the sample. We are trying to achieve epsilon delta success, and the question is how much computation time do we need, right? So first question is whether the task that we are faced with is realizable or not, or agnostic. Because it's easier to learn when you know that the data can be satisfied perfectly well by one of your examples, by one of your hypotheses. It may be harder in the agnostic case. Another kind of parameter on which we can separate or classify our problems is the question of whether we require proper learning versus unrestricted learning. So I mentioned it last time. By proper learning, I mean you have to output a hypothesis from the class H. By unrestricted learning, you can output any hypothesis that you want. It doesn't necessarily have to be in the class H. So if we look at these two axes, we can easily notice that if we move along this line, it will become harder. And also in this line, it's become... Oh, so let me change the order here. Put unrestricted here, unrestricted, and here proper. So harder will be again going from the origin out. So this will become harder, right? It's harder when I ask you, when I make more restrictions on your output. You have to output something from the class. So now in this table, where can we position the results that we've seen so far? So the first result that we have seen was learning rectangles. You remember? Learning rectangles in our N. And how did we, where was it seated, the rectangle learning? When we were learning rectangles, was the output that we gave by the algorithm, was it a rectangle or not? It was a rectangle, so it was proper. Now, did we require the data to be realizable, zero error over rectangle, or we did not? We did not, because you remember we said that we just go over all possible rectangles that are defined by the data. For each of those rectangles, we check its loss, and we output the one with minimal loss. So we did not have to assume that there is a rectangle with zero error. So learning rectangles was here, learning the class of H rectangles over RD. And we saw that in this most demanding corner, we could get here an algorithm that was running in time roughly O to O of D over epsilon square to the power 2D. That was the running time that we saw. That when you needed so much running time. Because this is kind of the size of the sample size that you need, and then you go over all 2D tuples from your sample size. So that was the learning rectangles. It was in this corner. Now, learning conjunctions was here. Why was it here? Because in order to learn conjunctions, we assume that the vectors that we get are realizable by some conjunction. You remember, we started with the all-term conjunction that included all possible literals. And then each time we eliminated terms that conflicted with one of our examples. And we're left with something useful just by the assumption that our training data is realizable. So that was here, and we can show something that was efficient, conjunctions over the variables. And what was the time that we needed here? And we output a conjunction. We just started with a big conjunction. We eliminated terms. What we were left with was a conjunction. So it was proper, but it was realizable. Right? And the running time just depended on the VC dimension. So we said that the VC dimension of these conjunctions was at most 3D. And we needed to just go over 3D examples one by one and eliminate. So it was something like O of d over epsilon. The sample size was 3D over epsilon, and we just needed to go over the sample size. Now, in the unrestricted case, still proper, we looked at the case of the 3-term DNF. In the 3-term DNF, what we showed is that, we claimed that you cannot learn it properly, but you can learn it in the unrestricted case by turning the 3-term DNF into a conjunction over a bigger space. So here it was essential that we used our ability to output something which was not in the class. So it was learnable here. And in fact, we cannot move any of them into a harder situation. So if we try to learn 3-term DNF in the agnostic case, we can show that this is hard, computationally hard. If we try to learn conjunctions in the agnostic case, it's become computationally hard. So we cannot move them. If we try to learn properly these guys, it becomes hard. So they cannot be moved into the more demanding scenarios. So what I want to talk about, the first thing I want to talk about today is some more formal statement of what do I mean by things becoming hard. In what sense is it hard to try to learn 3-term DNF in the agnostic case? In what sense is it hard to try to learn conjunctions in the agnostic case, and so on? So what do we mean by computational hardness? So we will talk about that there are different ways of indicating that the problem is computationally hard. We will talk about two ways here. One of them is NP hardness. So I don't know how much, what do we mean by NP hardness? I don't know how many of you have seen the term NP hardness? It should be everybody, right? How many people can give me a definition of NP hardness? Some of you. OK, good. So I don't care so much about the definition, but I want us to understand what it means. So NP hardness means, NP hardness is a kind of a relative notion of complexity. It tells us that unless there is a big surprise, in math or in science and computer science, there is no polynomial time algorithm that solves the problem for all inputs. So the NP hardness is some kind of a theoretical guarantee. It says the problem is as hard as many other problems that we don't know how to solve. But when we say we don't know how to solve, there is no algorithm that solves this problem for all inputs. It does not necessarily mean that there is no algorithm that will solve the problem on many inputs or in any input we care about. It just means that, assuming there is no big surprise, there is no algorithm that will solve the problem for all inputs. Now, let me just give you some. We will not prove any NP hardness, but this is considered a kind of a strong guarantee, a strong, I wouldn't call it a guarantee, a strong indication that there is no hope for a polynomial time algorithm to solve the problem. And for some of the very core problems that we want to solve, this is the case. So just some examples of NP-hard learning problems that we may care about. So let me start with something that we've already seen. So the first one is the axis-aligned rectangles. So we call it HD rectangles. If we wish the algorithm to be also polynomial in D. Because we know that we have here an algorithm, but this algorithm runs in time which is exponential in D. So you could ask, could I find an algorithm that its dependence on D will be better? Why do we care? Because if our data is in high dimension, we don't want, say the data has 30 dimensions, you don't want to run in time which is exponential, that has 60 in the exponent. That here is some input size, and here we have 60 in the exponent. So it would be very nice to allow us to have better dependence on the dimension, and unless p equals np, it will not be possible. And this is hardness result in the, we have now to say, we're talking about the realizable, are we talking about the unrestricted or restricted model? So this is going to be NP-hard even in the realizable case in the proper setting, if you want to output the rectangles. It is also hard in the non-proper setting, but then it is a little bit a weaker result. But so this seems to be like a very natural learning problem to learn rectangles, and it's already NP-hard in the realizable case if we want nice polynomial dependence on the dimension. And similarly, or not similarly, another very important problem, of course, is learning half spaces. And that's a problem we will talk about more in the rest of the course, because we will get into more and more practical algorithms, and learning half spaces is learning linear separators, right? Linear separators is a very important problem. And it turns out that here we can do it. It is easy in the realizable case. So if the data is such that you have the positive points and you have the negative points nicely separated, nicely separable by a linear separator, then it is relatively easy to find such a linear separator. But as we said, you remember that we had this example that we showed that most of the partitions, huge majority of the partitions, are not realizable. If it's not realizable, the problem becomes NP-hard. So NP-hard in the agnostic case and the proper, if you want to output the half space, and it's hard in some weaker sense also for unrestricted learning. So we see that yes?
If learning half spaces is easy in the realizable case, why is learning rectangles hard in the realizable case?
Yeah, that's a very good question. I mean, let me just repeat the question that everybody will hear. How can it be that finding a half space in the realizable case is easy, but finding a rectangle is hard, right? And the problem is, what is a rectangle in the realizable case? For a rectangle in the realizable case, you have pluses and you have minuses. And you know that there is a rectangle that will separate them nicely. Right? And it seems like, why would it be so difficult? I'll find a half space that separates nicely here. I'll find a half space that separates nicely here. And I'll continue 2D times, and I'll get a rectangle that separates my data nicely. So what could be the problem? So the problem, anybody sees what the problem could be? Why this may be harder than half spaces? Yes?
How do you know where that line is? Because, of course, some of the minuses are going to be on one side and some on the other side. Right?
Yeah, so the problem is that if I want to find the right line here, I'll have minuses here, you see? So say I have a minus here. How shall I describe it? The problem is that I don't know due to which coordinate is it a minus. When I see a minus, I have an attribution problem. I know that there is an interval in every dimension that captures nicely all of my positive points. But when I see a negative points, I know that it violates it's outside the interval in some dimension. But I don't know in which dimension. So this problem somehow forces me to check all combinations of dimensions and makes it exponential in the dimension. So in R2, it's not very difficult to check all possibilities. But in higher dimension, the problem is when I see a minus, it could be that this is a minus because I needed to put this line here. And it could be that this is a minus because I needed to put the line here. And when it's a high dimension, making those choices becomes combinatorially very complicated. I have to go over all possibilities, which kind of forces me into exponential indeed. So that's only an intuitive argument. I'm not giving you a proof. But what looks very nice in the picture in R2 becomes very complicated in higher dimension. And the problem is that when you see a minus, you know it violated at least one of the requirements on intervals, but you don't know which one. So you don't know where to choose the intervals. OK, good question. So we see, so learning rectangles is hard. We said hard in the proper realizable case. Learning half spaces become hard in the agnostic case. In the realizable case, it's still easy. So there's a complex landscape there. I would just mention one, and maybe the bottom line conclusion is that in the agnostic case specifically, even the simplest classes are hard to learn computationally. And that's going to be a big challenge to machine learning. Even the most natural classes, which is just a half space, just a weight for every attribute, are becoming NP hard once we are not assuming realizability. And realizability is not a realistic assumption. I just want to mention one more class which is NP hard to learn in the realizable case. Another one which is also NP hard to learn in the easiest case, in the realizable case. And that's the class of intersection of half spaces and even intersection of fixed number of spaces. So say intersection of k half spaces, and this is going to be hard, NP-hard, in the easiest realizable case as soon as k is at least 3. So we said we have this problem of, so what is this intersection of halves? It is almost like rectangles, but what I'm trying to find is such a partitioning. These are going to be the pluses, and these are going to be the minuses. So what I'm trying to find is I have a collection of points. They're labeled plus or minus. And what I'm trying to find is a collection of k half spaces. K is fixed, such that the intersection will capture all of the plus, as many plus points as possible, and all the minuses will be outside. And this is turned to be NP-hard even in the realizable case. And again, part of the problem is this attribution problem. Because half spaces in the realizable case are easy, but when I'm trying to combine them, it becomes very hard. And the reason I'm mentioning it is that we will get to this problem as a very natural learning task later. Later on, we'll see that it's a very natural learning class, intersection of half spaces. OK, so we have all kinds of hardness results that are NP-hardness results, and they are all about the proper, some realizable, some unrealizable. I want to mention one more tool for showing hardness, which is not NP-hardness. And this one is interesting for other reasons as well, and this is cryptographic hardness. So it turns out that there is a very close connection between learning and cryptography. It's like two sides of the same coin. In learning, you are trying to figure out what is the rule by which things are classified. In cryptography, you're trying to have a rule such that although the adversary may see some examples, he will not be able to figure out what is the rule that you are using. So cryptography can be viewed as the other side of the coin of learning, and we will try to make it a little bit precise for at least one example. So what is cryptographic hardness for learning? So cryptography, is the way that we try to hide data or hide information. Let me give you one example, and then we'll get from it to learning. So one example of cryptography, of the use of cryptography, is a key tool is one-way functions. So what are one-way functions? How many of you have heard the term one-way functions or seen it before? OK. Most of you haven't, I guess. So what are one-way functions? One-way functions are functions that are easy. It's easy to compute f of x from x, but hard to compute in the reverse direction, x from f of x. So a very intuitive such function is, say, the function, I don't know, x to the power 5. So if I give you a number, it's very easy to take it to the power 5. But if I give you the fifth power of a number and ask you what is the number, it's going to be hard. This is not hard for a computer, but it's hard for us. For us, even x squared, it's easier to take the squares than to find the square root. But there are functions, cryptography is based on the assumption that, so crypto is often based on the assumption that there are one-way functions in the sense that no polytime algorithm can invert them. I mean, you can think of one-way functions. If you want to think about it mathematically, we can think of one-way functions as a two-spaced tube. It's very easy to get the two-space out, but it's very difficult to get it back inside. So one direction is easy, the other direction is hard. Cryptography is based on the assumption that there are functions that are easy to compute, but no polynomial time algorithm can invert them most of the time. I will not get into a precise definition. It's sufficient for me to stay with this level of intuitive definition, but let me give you an example of where it is used. So for example, if you have your credit card and you have this stripe here, and you go to an ATM machine and you want to withdraw money, and they ask you for your PIN number. Now, as you probably know, it doesn't matter where you go in the world. You can go to Australia, you put your card, they ask you for your PIN number, you input your PIN number, it tells you whether it was correct or not. How does it do it? How does the machine in Australia know what is your PIN number? It is not reasonable to assume that every ATM machine in the world has a list of all the customers and their PIN numbers, right? It is also not reasonable to assume that they rely on communicating with your bank, because then it will take too much time and will break down every time the Wi-Fi is not working and so on. Another possible option is that on the stripe at the back of your card, you have your PIN number encoded. But that's also problematic, because then if someone steals your card, so if I have here my PIN 1221, someone steals my card, and they can just need a reader for the stripe, and they can use my card anywhere else. So how does it actually work? So the trick is that there is a one-way function which is common and known to all the ATM machines. And your PIN card is the input to this one-way function, and the output is what is written on the stripe on back of your card. So when you come to some machine in Australia and you want to withdraw money, the machine can read what's on the stripe. Then you enter your PIN. They can easily compute f of your PIN and see if it fits the stripe or not. But if someone steals your card, he has the stripe, he wants to withdraw money, he will come to a machine, the machine asks him for the PIN. And what he needs to do is to invert the function, which is hard. So one-way functions are really useful for authentication. If I want to make sure that it's you know your PIN, I can have the f of x written here. So here I have f of x, and your PIN is x. So it's very useful for authentication. But there is a problem if I want to use it to send you a secret message. Because if I use one-way function to send you a secret message, I take my message x. So here is my message x. And I use my function, and I send you f of x. So now I'm very happy. Nobody that will find the message will be able to decrypt and find x. But there is a small problem. What's a small problem? Yes?
That includes the person you send it to.
That includes the person you send it to. He will also not be able to decrypt it and find what X was. And that kind of defeats the purpose of the message, right? So in cryptography, we use some further construction, further assumption, and this is one-way functions, which we call trapdoor functions. So what are trapdoor functions? Trapdoor functions are one-way functions, but there is a secret key. That if you know the secret key, you can invert them. So you have, so f is a trapdoor function if one f is one way, but two, for every n, there is a key S of n such that it is easy to invert f of x on all inputs x which are of length, say binary strings of length n, given s of n. So if I give you as input s of n and f of x, then you can easily, in polynomial time, output x. But if you just give an f of x and you want to find x, then it's hard. So these are trapdoor functions. You have this secret. Yes?
For one-way function, if you know what f is, can you invert it?
No, you know what f is and you cannot invert. That's the whole point. Because all the ATMs in machine, they know what f is. And still you cannot invert it. So an example, like as a simple example of that, is what is called the discrete log. So the discrete log function is that I have some number. I mean, I will give you a very rough explanation. I have some number n, and your secret is x, and I compute n to the x mod some m. And now the problem, this is very easy to compute it. You take n to the x, and n is a natural number. This is a natural number. You can compute it, get the answer mod m. But to invert it is very difficult. Although you know that the function that I used is n to the x. To find which x would fit the exponent here is very difficult. So this is basically called the discrete log. It's like the log function. You want to find the log. But it's discrete because we're not getting real numbers. We're getting just bits of zeros and ones. Everything is encoded as zeros and ones. So the function is known, but it's still very difficult to invert it. OK? So these are trapdoor functions. Now, these are really used in cryptography. I mean, there is some secret. There is a way. So I can give you this code S of n, and now I can encrypt my message x and send you f of x, and all you have to know is this secret S of n and encrypt all my messages of size n. Now, what is the relationship to learning? So we can consider if I have a class of functions, if I have a class of trapdoor functions. So let f be, say, fn be a class of trapdoor functions over 0, 1 to the n. So what do I mean? I mean that fn is actually a collection of functions f of s of n, where s of n is a key for this function. So every such function has its key. And I know that without the key, it is difficult to invert, and with the key, it is easy to invert. Right? So now, let us see how we can phrase it as a learning problem. So assume you want to invert such a function. You want to break my code. So to break my code, you have to find my secret. Or you have to find s of n. Right? And so the point is that if you can generate a list of points, x1, f of x1, fs of x1, up to some xm, f of xm, and f is one of those secret functions. If you can get access to such a code, you can view it as a training examples for learning how to invert the function. Why is it training for learning how to invert the function? Because rather than using it, this as an input, as this is a label, we can view it the other way around. This is my input, and this is my label. So if you learn how to, given the input, find the label, you learn how to invert my function. So when you get such collection of pairs of messages and their encryption, if you get such a collection of messages, and you can learn, now I can learn the function. So I want to learn, what I want to learn is the class of all f minus 1 such that f belongs to fn. I want to find which function f minus 1 corresponds to the data that I saw. It will tell me how to invert it. So learning can be viewed as decrypting this code. And what is the VC dimension of this class? So the VC dimension of this class, we can estimate it just from the cardinality of the class. The cardinality of the class, we know that since s of n is polynomial, the code, the secret key is always polynomial in n. So we know that the size of such fn, if I have such a method for using trapdoors, the size of this is at most 2 to the poly n. Because every key is a binary vector of polynomial size. The number of such binary vectors is 2 to the length of the binary vectors. So I know that the VC dimension of such fn is polynomial in n. So the number of examples that I will need if I could learn this family efficiently, the number of examples that I will need will always be polynomial in n. So our conclusion, I mean, just giving you the intuition here without getting into technical details, is that if there are trapdoor functions, functions that are really satisfy the requirements of a trapdoor functions, then we know that there are classes that cannot be learned even in the unrestricted case. Here, when I'm asking you to decode, I don't ask you to find one of my functions. I just ask you find out what x was, what the secret message was. So I don't care what is the form of your hypothesis. I just want that you will have some hypothesis that in many cases will be able to find the message. So the assumption that there are trapdoor functions implies that there are learning tasks which are hard in the unrestricted case, when I allow you to output anything you want. And all the hardness results for the unrestricted case I mean, this is the easier case to learn. It's harder to show it's hard. All the hardness results for the unrestricted case are based on cryptographic assumptions. Assuming we have cryptography, then we can show that certain classes are hard even in the unrestricted case of learning. OK, so this is as much technicality as I wish to go into. And the main point here that I wanted to make is that we can see that if I give you examples, this is sometimes called the lunch break attack. The lunch break attack in cryptography is that you go out for lunch, I open the door to your office, and I look at all your messages that you already decrypted, and I see the message and the decryption, the message and the decryption. So I collect all of these, and now I want to be able to decrypt the next message. So that's exactly a learning task. This is X, this is the label of X. And you're trying to find the labeling rule, because the labeling rule will allow you to to decode secret messages. So these are two sides of the same coin, learning and cryptography. And when we want to learn to show hardness of learning in the unrestricted case, we have to resort to cryptographic assumptions, which in some sense, by pure theoreticians, they are kind of stronger assumptions than just NP hardness. But that's not our topic. OK, any questions so far? OK, so let's. This is as far as I want to talk about computation complexity of learning at this point. Yes, just a second. Yeah.
Are we given SN?
What?
Learning problem, or do we have to figure that out as well?
No, you have to figure it out. If you knew SN, you could decode the function.
So we know that we have some function that is in Fn, like capital Fn.
Right.
And we're trying to learn what Sn is.
No, you don't find out what Sn is, but you find out, I mean, you see, you don't find out Sn. You get x1, f of x1. And this is f of some s, but you don't know which s it is. You get xm, f of xm, same s. This was your lunch break attack. These are the messages that you find decrypted already on the desk of this person that you're trying, right? Now you're trying to learn how, given a next one, some fs of x, you want to be able to find x, right? So we can view it as a learning problem where this is instance and this is the label. Each one, this is the instance, this is the label. And what does the learning give us? Learning gives us a way that when we will see the next instance, we will be able to figure out its label with high probability. And figuring out the label is the same as decrypting, decoding the message. So you don't care if you know what is the S or not. What you care about is that you can invert the function. That on the next message, you will be able, seeing f of x, to find out what x is. So the only place where I used the keys, the SNs, is to say that this class of function cannot be too big. Because its function needs a key. The key has to be short, so there's only so much space on your key chain. So the class cannot be too big. OK? Any other questions on this? So what is the take-home message? The take-home message is that some very simple learning tasks may be hard even in the realizable case, let alone in the realistic unrealizable case. And computational complexity is a real bottleneck for learning. And that there are those kind of subtleties, whether it's proper or not proper, whether it's realizable or not realizable, can make a big difference. But even the simplest problems on the simplest classes are very computationally hard, and we have to find ways to overcome it. So what I want to talk, we are kind of switching gears now. Until now, the course was completely theoretical. And now, as we already seeing the end, I want to start giving you some cues about what do we do in practice. And the computational issue is a major issue in practice. So from now to the rest of the course, the nature of the course will be a little bit more practical, and we'll start talking about some major algorithmic approaches to learning. And by algorithmic approaches, I mean not classes, but really how do you run an algorithm that will do the learning for you. OK, so the first big learning paradigm that I want to talk about is boosting. So boosting is a learning approach that everybody in theoretical, all the people in theoretical machine learning are very proud of, because this is one of the few examples where something very practical grew out of pure theory. So what exactly was the boosting question? How did it turn from theory to practice? So there was we knew that there was this notion of pack learning. We are now living in the early 90s, 80s, early 90s. So it's how many years ago? 25 years ago. So we had the notion of pack learning. And people had all the fun about the fundamental theorem and the results characterizing it by VC dimension. And then they started asking about computation complexity. Of pack learning. And they realized that in many cases, many key, even basic cases, like half spaces, like rectangle, it is NP-hard. Right, so what was the problem that it's NP-hard? The problem is, as you remember, we were trying to learn as a function. We were trying to find a function of 1 over epsilon, 1 over delta, and some complexity parameter n, that it will be the runtime of your learning in order to achieve these kind of guarantees. And it turns out that this is going to be computationally hard. So people came up with the idea, when I say that something is NP-hard, to find a polynomial function like this is going to be very hard, maybe I don't really care about learning to any precision epsilon. Maybe it will be enough that the learning algorithm will give me something which is significantly better than pure guessing. So the hardness is based on the fact that you want to be able to, you look at the dependence on epsilon. How will your running time increase as the precision requirements grow? So the natural question was, what if we settle for what is called weak learning? And I'll define it in a second, but intuitively, weak learning means I don't want to succeed for any epsilon. I'm going to delete this epsilon parameter, the dependence on epsilon for my function. All I want is an algorithm that will give me advantage over random guessing. I'll be happy if I do better than random guessing. Will it allow me to overcome the computational complexity? So that was a question that people were asking, and this was the question that was posed to, there was a PhD student, Rob Shapiri. And he was asked this question for his PhD thesis, and Rob managed to show that it does not make life easier. So that was a very nice result. What Rob Shapiri showed is that if you can have, I haven't defined it yet. I'm just telling you the overline, the historical aspect of it. Okay, so he managed to show that it will not make life easier in the following sense, that if a problem is NP hard to learn, it will also basically be NP hard to weak learn it. So that's a very negative result. It's it should have been a pessimistic result. How can a pessimistic result become something of practical importance? But how do you show that weak learning is as hard as full learning? How do you show such a result? What he showed is that, and this is the boosting. The way to show it was by designing an algorithm that, given access to a weak learner, outputs a strong learner. And this is what is called boosting. This is the boosting algorithm. So a boosting algorithm is an algorithm that you give it access to a weak learner, and it works and gives you a strong learner. Why is it a negative result? Because it shows you that if you could find efficient weak learners, then run your algorithm and you will have an efficient strong learner. And those results show us that no efficient strong learners exist. So you can conclude that no efficient weak learner exists. So this is a completely pessimistic result, right? How can it turn into something useful? It turned into something useful because people say the boosting algorithm is wonderful. I mean, it takes weak learners and turns them into strong learners. Let's apply them in practice. Although the result was basically negative, this idea is really useful in practice because, sure, what you will get is not something which is guaranteed to always work, because something that's guaranteed to always work does not exist here. But it does give you a way of taking a weak learner, turning it into a strong learner. That's very useful in many cases. In practice, weak learning is easy. So that's the boosting algorithm. It grew out of this work of Rob Shapiri in his thesis. He was just interested in showing the negative result. A couple of years later, with Yoav Freund, or something, I'm not sure about the spelling of his last name, or something like this. Okay, they turned it into a practical algorithm, and it's one of the most useful algorithms in machine learning. So this is how theory became useful for practice, by ignoring the message of the theory. And this is the first type of algorithmic approach that I want to talk about. So we are going to define it precisely, what is weak learning, and introduce the boosting algorithm and show you how it works and show you that it's really something useful. Okay, so let us start with the definition. So our first definition is what is So our first definition is what is a weak learner. So a gamma weak learner, or let me say that a class H is gamma weakly learnable for some gamma between 0 and half if there exists a learner A, as usual, and the function m h gamma of delta, such that for every probability distribution d over x, and every f in H, seeing on a sample S IID generated by df, that is d picked points, and f is labeling it. We're in the realizable case, so we have a labeling function here. If we have such a sample of size greater than this m gamma h of delta, then with probability greater than 1 minus delta, the arrow L df of A of S is going to be at most half minus gamma. So it is like our usual definition of PAC learning, except that epsilon disappeared. Rather than having a function that will tell you how many examples you need for any epsilon and delta, all I'm asking you here is to get precision, which is arrow, which is at most half minus gamma. And notice that we are talking about the realizable case. So we know that there is a function in the class that has zero arrow. All I ask you is to get arrow less than half minus gamma, and we will be looking at the question that we focus on is the existence of efficient weak learners that is running in time polynomial in 1 over delta and some complexity parameter. So the epsilon disappeared. Instead of the epsilon, all I want to get is arrow less than half minus gamma. So that's my notion of weak learners. And let me give you the first example of such a class which is weakly learnable. I mean, my example will not be very impressive, but it's very useful. So an example of a weakly learnable class is the class of, so let H be the class of a 3 partitions of R. So what do I mean by this? Every H is the set of all H R1 R2 and plus and H R1 R2 minus, such that R1 is less than R2 and they are both in R, and H R1 R2 H plus R1 R2 of X is plus 1 if X is less than R1. It's minus 1 if X is between R1 and R2. And it's plus 1 if X is greater than R2. And H minus of R1, R2 of X is just minus H plus of R1, R2, X. So this is a very simple class. It's the class of all three partitions of the line. You label it plus here. This is R1. You label it minus here. This is R2. You label it plus here. Yes?
In the very last line of the H plus, shouldn't it be R greater than R2 greater than X?
X.
Sorry, never mind. I can't read.
You're talking about this?
I just can't read.
Ah, you just cannot read what I wrote? What I'm saying here is R2 is less than X. What's?
Should be greater than X. Oh, sorry, no, you're right.
No, I'm saying if X is here, it's plus. This is R1. If X is here, it's X less than R1. If X is between, then it's minus. And if X is above R2, it's a plus. So it's a plus minus plus. Did I make a mistake here or I'm okay?
You're okay.
Okay. So this is my class. It's a class of all three partitions of the line. And what I'm claiming here is that I want to show you that this class is weakly learnable by another class. So what I claim is that, so here I have a claim that, how did we call this class? Did we give it a name? This A, okay. Let's call it H3. H3 is third weakly learnable by a very simple algorithm, by ERM over a very simple class which is called decision stumps. So what are decision stumps? It is just a class of threshold functions. We will see in a minute why I give it a new name. But what I'm claiming is that if I do ERM over thresholds, I get a third weakly learning algorithm for the class of three partitions. So what is the claim? You get a sample. What do I have to show you to prove it? You get a sample which is labeled according to this three-way thing. Plus, plus, minuses, plus, 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 and so on. Now I want you to output just a threshold function. So, and I want to claim that there exists a threshold function such that the error of this threshold function is at most how much? So the claim is that for every a distribution D over R and every H in, or F, let's call it F, in H3, there exists a threshold function F. So F is just a decision. I pass a line, it's going to be plus on one side, minus on the other side. Just a threshold function F, such that the arrow with respect to D and F, the threshold function should get a different name, of H is at most half minus a third, which is 1 over 6. And 1 minus a third or a third, we will see in a second. Maybe I'll get an arrow third, so the gamma will be 1/6. So how do I show that such a function exists? Yeah, I'm sorry. This should be, I'm getting here just a third. So this is a 1 over 6, weakly learnable. So how do I get such a function H? You have some function which is a 3 partition. And there's some unknown distribution over the line. I want to show you that there is a threshold which is much simpler that makes arrow at most 1 over 3. So how will I find this threshold function? Are you quiet because it's too simple or because I got you confused? Yes. Right, so the main point here, I have a choice between 3 thresholds, or 4 even. I can label everything minus. I can label everything plus. I can put my threshold here. I can put my threshold here. But notice that I can always make sure that for any of those 3 regions, I can make sure that I err only on this region. If I want to err only on this region, then what will I do? If I want to err only here, which threshold should I pick? If I want to err only here, I'll pick the threshold that says I cut it here, I do all of this minus and all of this plus. What will be my error? My error will be only here. Right? If I want to err only here, what will I do? If I want to err only in the middle one, what will I do? Which threshold will I pick? Yes?
All plus?
All plus. All plus will err only here. If I want to err only here, which threshold should I pick? If I want to err only on this side, how can I find a threshold function that errs only here? Yes?
Put it at R1 and then do plus minus.
Put it at R1 and make this minus and this plus. Right. So for every piece of the 3 pieces, I have a threshold function that errs only on this piece. But there is always a piece that weighs at most a third. Because I divided my line into 3 pieces, right? So for every distribution and every such partition, there will be one piece that weighs at most a third. Okay, so therefore I can choose a threshold that will only err on this piece. Okay, so let me write it. The claim first. Note that for each of the 3 regions of f, there exists some h, which is the threshold, that errs only on this region. That's the first thing to note. Second, note that for any distribution D over R and any F in H3, there is a region of F that has the weight or probability at most 1 over 3. So I'll just pick, the ERM will just pick the third that weighs the least, and I can then find a threshold that will err only on this third. And therefore, my error will always be at most a third, which is a 6-weekly learning algorithm. Yes?
For the probability distribution D, is it usually over the domain, or is it
It's over the
slightly different when it's over the
No, no.
actual R?
No, it's over the domain.
Over the whole
My domain is R. But for every distribution over R and every 3 partition of it, there's always one of those 3 parts that weighs at most a third. Just look at the least probable of the 3 parts. Okay? So we can show, what we showed here is that sometimes simple classes can weakly learn more complex classes. And that's going to be the basic idea behind boosting. Okay, so now, before we continue, just one more comment. Yes?
But what if the distance between R1 and R2 is more than a third?
Is what?
It's more than a third.
No, I don't. There's no third. You see, there is the whole real line. There's the whole real line. And now you have the function f that has R1 somewhere here and R2 somewhere here. Now I ask you, what is the D probability of this part? What is the D probability of this part? What is the D probability of this part? D is a distribution over the real line. I took the real line and divided it into 3 parts, so one of the parts will have weight at most a third, because they add up to 1, and they are disjoint. I don't care about length at all. Length doesn't matter here. It's the whole real line. But I'm saying that for every such partition, one of the 3 parts will weigh at most a third. Now f gives you a labeling. Say minus is here, plus is here, minus is here. What I claim is that if you give me a third and tell me I want to err only on this third, I can always guarantee this with a threshold function. So I'll always have a threshold function that agrees on 2 parts and only misses 1 part. By agreeing on 2 parts, it gives you error of at most a third. Okay? So before we continue, just note one thing that, so yes?
Okay, so I understand what we showed was that there exists a threshold function that has this, but not
Right.
necessarily that ERM finds this threshold.
Right. But we need another step. That's a very good point. I only showed you that there exists a threshold function that makes error at most a third. But now we know that the VC dimension of threshold function is only 1. We can approximate the truly best by samples which are of size at most 1 over epsilon. And for samples of such size, we will get close to the error that we want. Yeah. Yeah, that's a good point. So just one more important theorem, actually, I can call it, but it's very simple. A class is weakly learnable if and only if it has finite VCD. And that's for any gamma. Is weakly gamma learnable, and that's for any gamma between 0 and half. It doesn't give us any new classes. The whole purpose here is to make things easier computationally. And why is that? One direction is clear. Finite VCD, finite VC implies spark learning, which implies weak learnable. And in the other direction, we know that infinite VCD implies we know that we have the sample size. If MH, we know MH of epsilon delta, we know that it is at least some constant times VCD of H plus ln 1 over delta divided by epsilon. So if the VC dimension is infinite, this is going to be infinite, even if here, instead of epsilon, I will put half minus gamma. It will still be infinite. So here I'll have half minus gamma, but if the VC dimension is infinite, I will still need infinitely many examples. So it doesn't give us any new classes. It is just a matter of computational efficiency. OK, so next time we will see some real boosting algorithms and how they are implied in practice.